which I will try to do today for sure, but I'll try to do it early on here. I've got chapter 7 up there. Chapter 8 I don't think has gotten posted yet. Okay, so in chapter 8 we have covered acids and bases, what they are, strong and weak acids, and strong and weak bases, and what distinguishes those. We've covered pH and the pH scale from 0 to 14. We've covered 3 critical equations to be able to use. The definition of pH, negative log of the hydronium ion concentration, how to convert hydronium ion, if you know the hydronium ion concentration, or if you know the pH, how to convert that into a hydronium ion concentration. Hydronium ion concentration equals 10 to the negative of pH. And then this Kw, this important dissociation constant for water, Kw equals 1 times 10 to the minus 14th, and it equals the hydronium ion concentration times the hydroxide ion concentration. It is a constant. So when one goes up, the other one goes down. They're a constant. The product of those two is always 1 times 10 to the minus 14. All right, so, and then we got into titration. All right, so there's, in a nutshell, the critical aspects of Chapter 8 on acids and bases. Titration, molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And so titration is designed to know 3 of those and to be able to calculate the 4th. It's a quantitative technique, analytical technique for determining the concentration of an acid or of a base. We presented it looking at it as the acid being the solution that we did not know its concentration. All right, so now the last concept is oxidation and reduction. This is a whole different kind of reaction. I ended talking about oxidation is the loss of electrons. Reduction is the gain of electrons. So that's your oil rig acronym, oil rig. Oxidation is loss of electrons, reduction is gain of electrons. In other reactions, precipitation reactions, acid-base reactions, there wasn't any exchange there of electrons. There's no change in the charge of things. But if we look at sodium reacting with chlorine to form sodium chloride, and if we want to balance that, two sodium atoms, if we want to go down to the atomic level, or 2 moles of sodium. But if we just want to look at it at the atomic level, what's happening here? 2 atoms of sodium react with 1 chlorine molecule to form sodium chloride. Now you don't see any charges there. Everything looks happy and neutral and all that. But what is actually going on? Well, we know that sodium has one valence electron. And it goes to form a sodium ion, and it loses an electron. Oxidation is loss. Sodium is being oxidized here. Sodium is the substance that's being oxidized. This is oxidation. And actually, 2 of these are producing 2 of these ions, and they're each losing an electron, if I want to work off of this balanced chemical equation. What's happening here? Chlorine, and I'm going to say what we got here. We got 2 chlorine atoms that look like that. I mean, here's what we know that looks like. There's the Lewis dot structure of the chlorine molecule. But the chlorine, individual chlorine atom is lacking an electron right here. This is why it is diatomic. It decides, well, I'm going to link up with another chlorine atom that is lacking an electron, and we're going to share these two, and we each have an octet. So there's your chlorine atom. Well, if you take 2 electrons here, they each gain an electron. You get 2 chloride ions. They're gaining an electron. That's reduction, or being reduced. And if you look at it, if you kind of look at the charges here for a minute, this thing has no charge on it. It's got an equal number of protons and electrons in the chlorine atom, no charge. It gains an electron and becomes negative. What happens? It goes from 0, no charge, down to a -1. It reduces in its oxidation number. So even reduction, I mean, this is kind of where it gets its name, reduction. Its overall charge is decreasing, reducing. And if you look at the sodium atom, it has no charge. It is actually going up. It's increasing. It's going from a 0 to a +1. So that is oxidation. This lower charge going down in charge is reduction. And why did it go down? Because it gained a negatively charged particle. The electron is negative. That -1 right there, it's got a -1 charge to it. An electron does. So when something gains an electron, it loses or reduces, lowers its oxidation number. So this is a redox reaction. And we would say that this sodium, this is the oxidation half reaction. And this is the reduction half reaction. All right? They never happen. Oxidation never happens without reduction happening. And notice that these electrons that I'm saying are really critical to this whole thing don't show up in the overall writing out of the chemical reaction. I'm writing out the chemical reaction here. You don't see any electrons. Well, the 2 electrons that these things lost, these things gained and became the chloride ion. So you don't. It's not like they went off in space somewhere. We don't know where these electrons are. They actually went from the sodium to the chlorine. So electrons don't ever go anywhere unless they got somewhere to go. Okay? All right? Someone say, Jose, where are you going? I don't know where I'm going. Jose, I know where I'm going. These electrons know where they're going. They don't go anywhere until they do know where they're going. They got a place to go. All right, so they don't show up in there. They're 2 are being lost, 2 are being gained. They balance them out. Those are the same 2 electrons. Those 2 electrons are the 2 that the chlorine are gaining. That's oxidation and reduction. It goes together. Goes together. It's like a debit and a credit out of a checking account. They go together. No oxidation reaction without a reduction reaction. Then we talk about reducing agent, oxidizing agent. The sodium ion is being oxidized. It is the reducing agent. What does that mean? It is the substance that is causing the chloride to be reduced. So it's the agent that's causing the chlorine to be reduced. So it's a reducing agent. Chlorine is the oxidizing agent here. It is being, it's an oxidizing agent. It is being reduced. Okay, so those are kind of opposite, or they kind of go together oppositely. The thing being reduced is the oxidizing agent. The thing being oxidized is the reducing agent. We call it oxidation because actually you can take just about any metal, and react it with oxygen, and the oxygen is the oxidizing agent, and it's causing the metal to be oxidized. You can take just about any metal. So initially, it was noticed that oxygen reacts with a lot of things and converts it into an oxide. And what's happening? The copper is going to, let's say, copper +1. It's losing an electron. The oxygen is going to the -2. But it's gaining 2 electrons. So the whole concept of oxidation and reduction is coming from oxygen's ability to oxidize many things. So that's where we got the name, oxidation reactions. But what you're seeing right here is chlorine. Chlorine can act like oxygen. It can gain electrons and be the oxidizing agent. Fluorine, bromine, other substances can gain electrons and be the oxidizing agent. Now, why are these reactions important? Well, you don't have to think about it very much until you get to the first thing that operates off of a battery, like your phone. Your phone's got a battery in it. The Tesla Model 3 has a battery in it. Electronic cars now, batteries in them. Charging stations where you can recharge the batteries on automobiles. What are batteries? Batteries are redox systems. That's what you got in any battery. Well, don't even talk about an electric car. Talk about starting your car. Start about going out to the parking lot and starting your car. You have a battery in there that is stored electrical energy to turn the starter on your automobile so that you don't have to go out in front of it like the old Model T and start your car. Okay? So the old Model T didn't have a starter. It had a driver. And the driver started the car by turning the engine over and getting it started. Well, your starter is doing that for you. So these are redox systems. Your car battery, I think lead and zinc in there, and they're actually going off of something like this. So I'm going to just take a guess here. Lead sulfate. This has a 0 charge. This has a +2 charge. And what the battery is doing inside the battery is separating these two things. So that what? So that you can have zinc going to form the zinc ion. Let's get that as a little n. and losing 2 electrons. And what do you have over here? You got your lead ion. It can gain 2 electrons and go back to be lead. So you have this potential sitting there for what? For electrons to flow from this cell of your battery to that cell of your battery. Electrons can flow. They're sitting there. The zinc is ready to give up those electrons to the lead, and the lead is ready to receive them. So what do you do right here? You put your starter in between those two. So you run a wire going from one side of your battery through your starter, through your key, through your switch to the other side of your battery. And when you turn the key, you complete that circuit and the electrons flow. You have an oxidation reduction system sitting there ready to be activated in your battery with a positive and a negative pole on the battery. Okay? So this is basically the concept behind any battery. There's a tremendous amount of research. You talk to Elon Musk, the CEO of Tesla, about batteries. And I don't know where is it. It's in Arizona or Phoenix or somewhere. He's building one massive, huge plant that is going to be able to manufacture as many batteries as the world produces right now. That one plant is going to be able to produce more batteries than the capacity of all countries making batteries. He's committed to batteries. He's committed to electronic ways of running things, homes, cars, and lots of other things. So, and those are oxidation reduction systems. The lithium battery system, these are oxidation reduction reactions. So yeah, corrosion is an oxidation reduction process. Burning fossil fuels is a redox reaction. Things are being oxidized and reduced. Bleach. Okay, why is bleach so much more powerful than a detergent? Detergent is just emulsifying the oils in the dirt and getting it off the clothing. Bleach is going after the dirt and reacting with it. And you leave your clothes in there too long and it goes after your clothes. So this is a much more aggressive chemical reaction going on with bleach than with detergent itself. So those are some of the importance of oxidation reduction. I meant to kind of take a peek at the exam to see what kind of things are going on in there, but we had, I think the homework in Chapter 8 talks, and another chapter talks about types of reactions. There's one of the homework assignments that talks about precipitation reactions, acid-base reactions, and oxidation reduction reactions. So how do you distinguish those? Well, a precipitation reaction, and the one the example we've used the most is this one. This was also in the lab. If you look at this equation, everything this starts out with a +2 charge. How do I know that? That's a -1. If I move this 2 right up there, that's a +2 iron. Well, it stays a +2 iron. And the critical thing that identifies this as a precipitation reaction is that. Everything else will say aqueous. All right, so that's a precipitation reaction. Here's an acid. How do you know it's an acid? Well, you look, HCl, that's a strong acid. Here's a base. You see the hydroxide right in the base. and you're going to get sodium chloride, and you're always going to get water in an acid-base reaction. And again in here, nothing is changing charges. You got an OH over here with a -1. The hydrogen is still a +1. You got a hydroxide over there. So what I'm pointing out here in precipitation and acid-base reactions, there's no exchange of electrons. Something's not giving up an electron and becoming more positive. Something's not gaining an electron, becoming more negative. They're just rearranging themselves into new compounds, but they're maintaining their original charge. But if you start something like this, here's nitric acid. So you say, oh, there's an acid. Is that an acid-base reaction? No. What else do we get here? Hydrogen? I think so. So this has no charge, and it's ending up with a +2 charge. This has a +1 charge, and it's ending up with no charge. Elements have no charge. So here's an element, copper, in its elemental form. Here's hydrogen in its elemental form, no charge. So there's charges are changing. Something is changing a charge, so that gives you an immediate idea that it's an oxidation reduction reaction. The only way those things are going up and down in charge is because electrons are moving. Electrons are moving from one thing to another. So at bare bones, just kind of be able to distinguish. Those are three main types of reactions, and they're in their own little category. We don't have an acid base here. We have a precipitate being formed. We do have an acid and a base here. It's a neutralization reaction. And even though we have an acid here, it's reacting with a metal to form a soluble form of that metal, an ion, and that's a redox reaction. Okay, so that's chapter 8, and the last slide was just kind of alluding back to acids and bases. Any comments on chapter 8? We can come back to it when we kind of do our review.